Another problem that you'll come across is a molarity type problem. How would you attack a problem like this? Well, here you're given a typical problem like you're given a mass of a solute, given the total volume, calculate the molarity. This is much easier than the last problem. Here you just have to convert them, recognize that the sodium hydroxide is the solute. What is dissolved in the solvent? The solvent is the water. So 36.0 grams of sodium hydroxide converted to moles would be done like this. 36.0 grams times or essentially dividing by the molar mass of sodium hydroxide, which is exactly 40.0 grams. But notice how the units, this is how you should practice these problems. Make sure the units are converting properly. Grams on top cancels with grams on bottom. I'm left with moles of sodium hydroxide. That divided by the molarity, or the volume of the whole solution, 1.50 liters, is my molarity, moles per liter, which I can express as this square bracketed sodium hydroxide, like so. That's a pretty easy problem. Here's a dilution problem. Here, let's say I give you something like this. I say you have 50 milliliters, 50.0 milliliters of 12 molar HCl. That's a strong acid, very concentrated. I say add 250 milliliters of pure water to it. Mix them together in some larger container. It would have to be a container at least 300 milliliters in volume, otherwise it would spill over. What is the concentration of this acid after you mix it? Well, it's obviously going to be less than 12 moles per liter because I'm diluting it. But what is it? Well, some people think, well, it's just 50 to 250. I'm diluting it by 5. So that would mean that the answer would be 12, the original concentration, divided by 5, which would be 2.4. But they'd be wrong. The reason why they're wrong is because they're not reading the problem correctly. I'm not diluting it to 250 mils. I'm adding 250 mils of water. So my total volume is actually the sum of this volume and this volume, which is 300 milliliters. So read the problems very carefully. So you can use this dilution equation. M sub C, V sub C, molarity of the concentrated solution times the volume of the concentrated solution equals the molarity of the diluted solution times the volume of the diluted solution. Again, all that is saying is that moles of solute is the same before and after. It's not changing. The moles of HCl before you mixed it is the same here, and it's the same when you combine the two. So that's what this is saying. So I would solve this equation for my molarity of my diluted solution, M sub D. But I'll just call it M sub HCl here. So it's the initial concentration of 12.0 moles per liter, M sub C. It's my volume of my concentrated solution that I used, which was 50.0, divided by, move the V sub D over to the left side, divided by the volume of the diluted solution. The volume of the diluted solution was the sum of these two numbers, 50 plus 250, which is 300. Notice I can leave it in milliliters because 50.0 milliliters on the top cancels with the unit milliliters on the bottom, and I'm left with the units of moles per liter, which is what I'm after. That is molarity. So you don't have to change the unit of volume in this equation. As long as you use milliliters on both sides or liters on both sides, or whatever unit you want, you're fine. The more classic way to do it would be to convert everything to liters. So 50.0 milliliters, move the decimal 3 to the left by dividing by 1,000. 50 divided by 1,000 is 0.05, 0.0500. Keep all the sig figs. I'd like you to do that. That's that in liters. Times the, same thing here, I'm just doing it in liters, times 12.0 moles per liter, divided by this number, the sum of the two volumes, but now in liters. 300 mils is 0.3000 liters. Notice now the units cancel, I guess, like this, or this, or this and this, but you're left with moles per liter. Same thing. It's got to work. 2.0 molar. So it makes sense. You've cut the concentration by a factor of actually 6. 50 to 300 is a factor of 6, right? Let me make sure that is true. I'm sure that is 6. So you've cut the concentration by 6. 12 divided by 6 is 2. Another problem that we just talked about a little bit in your textbook is combining this definition of molarity, moles per liter, combining that with stoichiometry problems where you're calculating how much stuff you get out of a chemical reaction. So remember when we were talking about Chapter 6 material, we'd give you mass of a reactant. We'd ask you how many grams of a product do you get. Well, you can do the same type of problem now with liquid aqueous solutions. So instead of giving you mass of a reactant, I give you volume and molarity of the solution. But remember, when you combine those two, you can get moles, which is the same thing as saying grams, because m moles is equal to molarity times volume, when this is moles per liter, and that's liters. That gives you moles. So it works out. This is just an indirect way of giving you amount of something. So Clumsy Carl spills 50.0 mils of 5.0 molar sulfuric acid, a very strong acid, all over his lab bench. That's not a good thing. His instructor tells him to neutralize the spilled acid with baking soda. Baking soda will neutralize acid. Base plus acid will make water and some relatively harmless salts. So the question is, how many grams of baking soda should he pour on the acid spill to completely neutralize it? This is a stoichiometry problem in disguise. So the first thing you have to do, if you remember, is you always have to write a balanced reaction. The balanced reaction that's going to occur when you mix sulfuric acid with sodium bicarbonate is this one. 2 moles of sodium bicarbonate solid plus 1 mole of H2SO4 aqueous concentrated or sulfuric acid will give you, it's a double displacement reaction. Sodium goes with sulfate to give you sodium sulfate. Hydrogen ions from the acid combine with HCO3 to make H2CO3, which actually would decompose into water and CO2. You would see CO2 bubbles coming out of this reaction. We don't have to worry about that right now. All we have to worry about is balancing it. So you'd have a 2 here, a 1 here, a 1 here, and a 2 here. So once you've balanced it, what you can do is jump right in and solve the problem. You're trying to get how many grams of this stuff do you need? Well, you take the given information. I know the volume and the molarity of the sulfuric acid, so I can solve this. I can convert the volume and the molarity to moles by multiplying them. But now I have to convert the 50.0 milliliters of acid to liters by dividing by 1,000. So milliliters on top cancels with milliliters on the bottom. I have liters times moles per liter. So liters here cancels with liters on the bottom. I'm left with moles. So volume times molarity, again, gives me moles of my acid that I spilled, 0.25 moles. Well, I see there's a 2-to-1 ratio, so I really need twice as many moles of baking soda. So twice that number, 0.25 moles of sulfuric acid times the ratio 2/1, which I'm just reading the balanced equation. Excuse me. 2 moles of baking soda for every 1 mole of this. So I have moles of sulfuric acid on the top cancels with moles of sulfuric on the bottom. 0.25 times 2 is 0.50 moles of baking soda needed. So now I have that. I'm almost there. How many grams do I need? Well, just convert this to grams. 0.50 moles of baking soda, NaCO3. Multiply this by the molar mass of this. Add up a sodium atomic mass to a hydrogen to 3 oxygens, you get 84. So 0.5 times 84 is half of 84, 42 grams. Again, that makes that's a good amount. That's about the amount of sugar that's in a Coke can. It's a handful of baking soda that would neutralize a relatively small spill of acid on a table. So I do expect you to be able to do a problem like this. Again, if you need to go back and review stoichiometry about how to convert moles to grams and grams to moles, please do so. That's chapter 6 material. But again, it's really the same problem, just with that extra step of converting volume and molarity to moles. So that's the type of problem that we'll be working on in your next homework assignment. The next lab I'm going to have later in the week is an acid-base titration lab. So please watch these videos carefully. Do as many homework problems as you can with Chapter 9 material, but I've given you all the major type of problems that I want you to work on, but there are more specific ones or more problems, more options for you to do in the textbook. And then start reading Chapter 10 as well. The next videos I put online tomorrow will be on acids and bases. But now that you have a firm foundation of what solutions are and how to express concentrations, we can move into studying what is called pH of a solution, concentrations of acids and bases. And that will be, again, Chapter 10 material. So please start reading that as soon as you can.